Okay, this is part two of the neural network discussion. Um, Let me just show you, I think it's good to show you some pictures here, if we can find them. This is a picture of a neural network. Um, and there's one more picture they have here, which is kind of a little bit more standard looking picture. I don't know if I can find it right now. It's at the end. This one. Um, so this is kind of what you usually see as a neural network. So in this case, let's look at this a little bit. Uh, no, not shrinking, is it? Okay, let's look at this. Um, so if you look at this picture, uh, you have what these are all called nodes. You have these squares, these circles are called nodes. And here we have what this first set of nodes is called the input nodes. And the second set of nodes is called the hidden layer. And the last set, actually there's only one, is the sort of looks like there's two, but there is the output nodes. Okay, so that's basically what we think of. That's kind of the picture we think of when we have a neural network. So what you're, for example, this is an example. In this example, what they're doing is they're taking a bunch of data. So the data is sort of given here. So a person's age, their education, their race, their gender, something about their capital gains, whether they have a capital gains or capital loss, the number of hours they work per week, uh, what kind of job they have, so government, self-employed, private, the information is missing, their marital status. So I guess that's all, right? There's nothing else here, yeah. So they're taking that data, and with that data, they're trying to predict their income. Not exactly precisely their income, but whether their income is less than $50,000 or greater than $50,000. So that's a neural network. That's a problem that you could try and do with a neural network. So over here you have the input, and here you have the output. And as I said before, this is called the hidden layer. And so for each variable, you have a node. And we'll see how this works. But anyway, for each variable you have a node. So for age, you have a node. For education, you have a node. For race, actually, we have split it up into race white, race black, race Asian, race American Indian, race other. And we were just talking about this in the last video. Um, so if you have a categorical variable, by the way, that's also called in some books or some fields they call it a level. Sorry, no, they call it a factor. And these are the different values that, for example, race can be, in this case, white, black, uh, Asian, Pacific Islander, American Indian, Eskimo, or other. So that's the way they divide up race. And so what they do is they set each one of these as a yes-no variable. So yes-no to white, yes-no to black, yes-no to this, yes-no to this, yes-no to this. Okay? So when you have a categorical variable, usually for a neural network, you'll split it so that each value becomes an input. Okay, just like they do the same thing with gender. For male, they have one, and female, they have a second one. Now, okay, and so that's what this looks like. All right, let's go back to uh, the previous discussion. But before we do that, this is a simpler one, isn't it? Uh, so here you only have 3 input nodes and 2 hidden layers and 1 output. Now we didn't talk about what the hidden layer does, but we will. Okay, so clearly since neural networks produce continuous output, they may quite naturally be used for estimation and prediction. Suppose, for example, that we are interested in predicting the price of a particular stock 3 months in the future. Presumably, we would have encoded price information using the min-max normalization above. However, the neural network would output a value between 0 and 1, which one would hope does not represent the predicted price of the stock. That's a joke. So anyway, but it'll output a value between 0 and 1. Rather than the min-max normalization, rather, the min-max normalization needs to be inverted so that the neural network output can be understood on the scale of stock prices. In general, this denormalization is as follows. So the prediction is the output times the data range plus the minimum, right? So, for example, let's see. Well, they have an example here. Where output represents the neural network output in the 0-1 range, the data range represents the range of the original attribute of values on the non-normalized scale. So like the original price of stocks, the range of the price of stocks. And the minimum represents the smallest attribute on the non-normalized scale. For example, suppose that the stock prices ranged from $20 to $30 and that the network output was 0.69. So how do we, what's the price that we're predicting here? It's not 0.69, even though that's what the neural network predicts. So how do we translate that into the actual price of the stock? So we take the range was 10, right? 20 to 30 is 10. So we take 0.69 times 10, which gives us $6.90, plus the minimum, which was 20. So we get 26.90 is $26.90 is the prediction if the neural network gave us 0.69. So the neural network output is going to be between 0 and 1. Then we have to sort of denormalize that, as he says. Okay, so here's the example, and let's take a look at this and see how it works. Let us examine the simple neural network shown in figure 7.2. A neural network consists of a layered, feed-forward, completely connected network of artificial neurons, or nodes. So we'll sort of understand what these words are. The feed-forward nature of the network restricts the network to a single direction or of flow and does not allow looping or cycling. So we're going to sort of feed the information through this direction and not sort of allow for kind of cycling. The neural network is composed of 2 or more layers. In this case, there are 3 layers. Although most neural networks consist of 3 layers: an input layer, the hidden layer, and the output layer. There may be more than one hidden layer, although most networks contain only one, which is sufficient for most purposes. The neural network is completely connected, meaning that every node here is connected to every node here, and every node here is connected to every node here, and you can see that that's true, right? So every node, every one of these nodes is connected to every node here. And so this node is connected to both of these, and so on. Although not to, but they're not connected to nodes in the same layer. So that's called completely connected. Each connection between nodes has a weight, W1A, associated with it. Uh, at initialization, these weights are randomly assigned to values between 0 and 1. Um, this node is connected to this node, and to this node. And we have this line, and we have this line. And there's a weight associated with this line, and that's labeled W1 because it's the first node here, A because it's the node A here. And then there's a weight associated with this line, and that's called what? W1 because it's this node, and B because it's connected to this node. For example, this one would be what? W3A, W3B. So that's the way he's labeling these so-called weights. And same thing here, WAZ, WBZ. What we do, it's kind of strange, but you'll see how it works. But what we do is we assign all of these weights at random at first, but we just at random between 0 and 1. And the number of input nodes usually depends on the number and type of attributes in the data set. Well, we just saw that before in the other example. The number of hidden layers and the number of nodes in each hidden layer. So the number of hidden layers, in this case we just have one hidden layer, and the number of nodes in each hidden layer, so this hidden layer has 2, but we could have like 4 hidden layers and each one could have a different number of nodes in it, are both configurable by the user. One may have more than one node in the output layer depending on the particular classification task at hand. How many nodes should one have in the hidden layer? Since more nodes in the hidden layer increases the power and flexibility of the network for identifying complex patterns, one might be tempted to have a large number of nodes in the hidden layer. On the other hand, an overly large hidden layer leads to what's called overfitting or memorizing the training set at the expense of generalizability to the validation set. So what that means is that if you have lots of nodes, you're going to be able to, you'll see sort of that you'll be able to fit the data very well. You'll be able to predict the data that you have very, very, very well. The more nodes you have in there, the better you'll be at predicting the data that you have. But you'll probably, as you get, but because the data that you have hasn't so-called noise in it, has some randomness in it, what you're doing is you're fitting the model to that noise, to that randomness as well. And so when it comes to predicting new data, it's not going to be as accurate because you fit it too closely to the noise. So that's what he's saying here. If overfitting is occurring, one may consider reducing the number of nodes in the hidden layer. So if you find that you're overfitting, then you can reduce the number of nodes. Conversely, if the training accuracy is unacceptably low, one may consider increasing the number of nodes. So let's remember that. Okay, so if your training accuracy is not so great, you might consider increasing the number of nodes. And you can do that with Weka. We will investigate the structure of hidden layer nodes and the output layer nodes using the simple data provided in table 7.1. So here is the table. So what does that mean? So we have x0 equals 1, x1 equals 0.4, x2 equals 0.2, and x3 equals 0.7. Now, so let me ask you, how many records does this represent, that what I just read? It only represents one record. If you go back to that other picture, well, first of all, what do they mean by x0, x1, x2, x3? they mean this. This is the x0, x1, or actually no, this is x1, x2, x3, x0 is a sort of separate one. We'll talk about that in a second. So we're saying that what goes into here, this first node, is 1. What goes into here, second node, is 0.4. Oh, I did it wrong. I read it wrong. It's x1, so x1 goes here. x2 is 0.2. That goes into node 2. And x3, 0.7, goes into node 3. And x0 we'll talk about in a second. Um, so, so what I asked you is how many records does this represent? Well, think of this, maybe this is a person's height and their weight and their um, number of sandwiches they eat per week. Okay, so we just have one value for this, one value for this, and one value for this. So in other words, we have a weight like 150 or what are 60 kilograms, and a height 175 centimeters, and the number of sandwiches 10 sandwiches per week. Okay, so how many records does this represent? It represents just one record, just one person, right? So we're only talking about inputting one record here. Okay, and the weights we said were randomly assigned, so these are all randomly assigned, and they're all between 0 and 1. They say first, a combination function, usually a summation function, produces a linear combination of the node inputs and the connection weights into a single scalar value which we will term net. Thus, for a given node j, net j is equal to this. What they're saying is very simple, actually, just that we're going to take, for example, we're going to say, what comes into node A? Well, node 1, node 2, and node 3. And then what we're going to do is we're going to take node 1 times this weight plus node 2 times this weight plus node 3 times this weight, and that's what's going to go into node A. So we're going to take the node values here times the weights and sum them all up for all the nodes, and that's the input into node A. So that's what he's saying here. So we take what goes into the jth. Jth would be, for example, this one, node A. What goes into node A? So it's Wij plus times Xij. So thus for a given node J, so for example node A, what are we going to do? What's I? So I is here it says, and there are I plus 1 input nodes to node J. So that's just how many are downstream in the previous layer from node J. So that means I would be how many inputs are there into this? So there's 1, 2, 3. Actually, there's 4 because we have one extra one which we haven't talked about. So, but basically we could say there was 3. But we have this one extra one which we didn't really talk about. So we have x0a, x1a, x2a, all the way up to xia, or x in our case x what? x3a, or w3 W3A. So we have, for example, W1A, W2A, W3A. Are they using the same order here? IJ, yeah, they are. So J is this node, and I represents this node. Okay, so that's all this says. So let's read it. Thus, for a given node J, net sub J equals sigma Wij Xij. So the notation is a little bit confusing, but not really. So the J's remain the same because we're talking about for a particular, like A, net A. And then we want to sum over all the previous downstream nodes. Wij represents the weight associated with the ith input to node J, and there are I plus 1 inputs to node J. Note that x1, x2, xi represent inputs from the upstream. Is that called upstream? Oh, maybe I used the wrong word. Maybe it should be called upstream nodes. While x0 represents a constant. So here's what the x0 is. Represents a constant input, analogous to the constant factor in regression models. So, which by convention uniquely takes the value 0, x sub 0 j equals 1. So we're going to set it to 1, and then the weights will be adjusted so that it may not be the product of the weight times that 1 will not necessarily be 1. And this is kind of like a constant term. Thus, each hidden layer or output layer, node J, contains an extra input equal to a particular weight W0J, X0J. But since we're going to set X0J to 1, then really this is just W0J, such as W0B for node B. Okay, so for example, for node A in the hidden layer, we have net A. So they're asking, given this set of data, what's going into node A? What's the input into node A? So what is it? So you just take, we're going to set x0, we're going to arbitrarily set it to 1. So what goes into A? So it's this times this, plus this times this, plus this times this, plus this times this, right? So that's what they say. So it's, now there might be an error here. I think I spotted an error once here. Is it right? 1 times 0.5, sorry. And x1 is 0.4 times 0.6. That's okay. And 0.2 times 0.8. Okay, that's okay. And 0.7 times 0.2. Okay, that's okay. I wonder if this actually adds up to 1.3. That might actually be the wrong. You might have made a mistake there. I forget. Anyway, that's the idea. Within node A, this combination function net A equal to 1.32 is then used as an input on an activation function. So now, so we just said that's what's going into the node. So what's going into the node is 1.32. And then now we're going to sort of process that 1.32 in here and then spit out some result as an output to this node and do the same thing, multiply that new output times this, and so on for all the nodes. So how do we process this input? So there are lots of different ways you can do it. It's basically an infinite number of ways that you can do it. But certain ways seem to work. work well or work better in terms of making good predictions. And remember, that's the end result is we're trying to make good predictions. So let's see what their ideas are about how we might process that input. Within node A, this combination function net A equals 1.32 is then used as an input to an activation function. In biological neurons, signals are sent between neurons when the combination of inputs to a particular neuron crosses a certain threshold and the neuron fires. This is nonlinear behavior, since the firing response is not necessarily linear related to the increment in the input stimulation. What does that mean? So all he means by that is, so what are we going to do? We're going to get the inputs from here into here, which we just called net A, and then we're going to have to decide when and how much to output here. So what he's saying is sometimes if these are actually neurological or biological neurons, what happens is the input comes into here, and then the amount that's output here is not linearly related to the input here necessarily. And also, it may not even fire at all. If it doesn't reach a certain threshold in terms of the input, then this may not even fire at all. Okay, so that's what he's saying. Let's read that again. In biological neurons, signals are sent between neurons when the combination of inputs to a particular neuron crosses a certain threshold. So if it doesn't cross the threshold, it won't even fire, and the neuron fires. And also, this is nonlinear behavior. So the amount, once it reaches the threshold, it's not even linearly related. The output is not even linearly related to the input, even at that point. Okay. Artificial neural networks model this behavior through a nonlinear activation function. But still, there's so many different possibilities. Which one do they use? So the most common activation function is the sigmoid function. Y equals 1 over 1 plus e to the minus x. So this is obviously a function. Y depends on x, obviously. Right? So you put in an x, you get out a particular y. And if you graph this function, let's see what it looks like. It looks like this. That happens to be what the graph of that function looks like. So how is this being used? So what happens is, remember, x is the input that comes from the, what do they call them, the upstream nodes, and y is what gets spit out on the other side of node A, for example. So how does this work? So what we're saying is, if x is between, like if x is here, how much gets spit out? Not very much. Okay? If x is here, how much gets spit out? Like this much. If x is here, how much gets spit out? This much. Okay? So that's sort of what we're saying here. Now actually what they're going to do, I think, is they're saying here, this symbol here is saying only when it gets, when the output is greater than 0.5, do we actually even spit out anything. Otherwise, even though the output is 0.4, we don't actually even use it. So, that's what they mean here. So it's there's a threshold, which is 0.5. If it doesn't get past 0.5, it doesn't even get spit out. And it's still, even if you, so what x do you have to get as input in order to get 0.5? I guess it's this one, 0. So when x is 0, then you get enough to spit something out. But as x increases from 0 to 5, the output is not linear, right? Like when it goes from here to here, it increases from here to here. It kind of increases a lot, as compared to when it goes from here to here, it only increases a little bit from here up to here, only a little bit of increase in y. Okay, so it's not linear, the output. Uh, so that's the function we're using. Okay, so they say the most common activation function is the sigmoid function. It's called a sigmoid function, where E is the normal E. Thus, within node A, the activation would take place, would take net A equals 1.32 as the input. So for our data that we gave, that one sample piece of data that we had, represented by table 7.1, we got a net A of 1.32. So that's the input to the sigmoid activation function, and produce the output. So you put in 1.32 into here, and this is what you get. Node A's work is done now for the moment, and this output would then be passed along the connection to the output node Z. So that's what gets output. If this reached the threshold, which I guess it did reach the threshold, or they're saying it has reached the threshold. So if it reached the threshold, then this would be output. So in other words, what was that again? 0.7892 would be the output from here, and then you can imagine doing the same thing here and here to get net Z, right? The input to node Z, net sub Z. So anyway, what would be output would be 0.7, whatever that was, for node A. Okay, node A's work is done. Okay, where it would form via another linear combination a component of net Z, right? But before we can compute net Z, we need to find the contribution of node B. So remember, we want to get net Z. So now we're saying what's going to be put into here. So we already figured out this part, or we figured out this part, then we'd multiply it times the weight. And now we need to figure out what this part is and multiply it times this weight to figure out what's going to be input into node Z, or what we call net Z, net sub Z. But before we can compute net sub Z, we need to find the contribution of node B from the values in table 7.1. So we go back to those values again. And if you want to go back, you can see them here. Go back to these values, and you can do a new calculation. Where is it? Here. And you get the same kind of calculation, and that's going to be 1.5. So that's the output from, that's the input into B, and then we have to take that input and put it again into the sigmoid function to get its output, and it turns out to be that. Then node Z combines these inputs from nodes A and B through net Z, which is a weighted sum. So we take these and we use the weights. Using the weights associated with the connections between these nodes, note that the inputs xi to node Z are not data attributes, right? Because the data attributes have already been processed, and we got the inner layer, the hidden layer rather. The data attributes, remember, are here. This is where the data attributes are input. So these are no longer data attributes per se. But the inputs from the sigmoid functions from the upstream nodes. Finally, net Z is input into the sigmoid activation function in node Z, resulting in this output. So this output is the output from the neural network for the first pass through the network. Okay, so now you can see that, okay, we chose the sigmoid function, but we really could have chosen all kind. We're trying, in a sense, you could say we're trying to model what's happening in a biological neuron, and obviously this is not exactly what happens in a biological neuron, and we could use other functions or all kinds of other ways of sort of calculating how to output from a particular input. But anyway, it's commonly, the sigmoid function is commonly used. Okay, so how much data have we processed so far? We've only processed like one record. Like if you go back to that other picture, if you go back to this picture, we basically have only processed one person. Like we put in their age and their education and we filled out all of these. So we got all these nodes and we got all the weights and we did all this and we did all this. And we got one person. We've only processed one person. But presumably we have like a data of like maybe 1,000 people or 10,000 people, right? So we'd want to do this for each person. But there's one more step that we have to follow. But before we do that, let's just discuss the activation function a little bit more. So why use the sigmoid function? Because it combines nearly linear behavior, curvilinear behavior, and nearly constant behavior. What are they talking about? Well, that's a common way to describe this sigmoid function. If you look at it in this range here, it's kind of linear. If you look at it in this range over here, it's kind of constant. It's almost constant. Okay, and here it's, I guess we could call it curved or curvilinear. And here it's almost constant, and here it's curvilinear. So it combines all of those, they say. And it's a very popular function to use because of that. Depending on the value of the input. Figure 7.3 shows the graph of the sigmoid function for x between -5 and 5, although f of x may theoretically take any real valued input. Through much of the center of the domain of the input, for example, between -1 and 1, the behavior of f of x is nearly linear, right? So if you look at only between -1 and 1, it's pretty linear. As the input moves away from the center, f becomes curvilinear. By the time the input reaches the extreme values, f of x becomes nearly constant. Moderate increments in the value of x produce varying increments in the value of f of y, depending on the location of x. So, depending on where you are, you get different amounts of change, right? Near the center, moderate increments in the value of x produce moderate increments in the value of f. However, near the extremes, moderate increments in the value of x produce tiny increments in the value of x, in the value of f of x. The sigmoid function is sometimes called a squashing function, since it takes any real valued input and returns an output bounded between 0 and 1. So it's this function is bounded by 0, right? It never goes, this line never goes below 0, and it never goes above 1. So it's a squashing function since it takes any real valued input and returns an output bounded between 0 and 1. So there's, there's plenty of research to be done in terms of using other functions and seeing how well they work, but this is what's being used a lot. Okay, so Now, we said we put in only one set of data. Only one record from a set of data. So if we just went and did this again, um, the well, that's not what we do. Nothing would be accomplished really by doing that. The question is, how does the neural network learn? Neural networks represent a supervised learning method requiring a large training set of complete records, including the target variable. So remember what this means. We have a set of data. For example, if we go back to that predicting people's income, presumably we have, let's say we have 10,000 records. And in those records we have people's age and their race and all that other data, and we have their incomes for those 10,000 people. So you'd say, well, we don't need to predict their incomes if we have them. And that's right. We don't need to predict their incomes if we have them. What we're doing is we're using those 10,000 records to build a model, and then if we get a new piece of data where we don't have their income, we can take just the inputs, just the age and the gender and the race and so on, and make a prediction. But we have 10,000 pieces of data where we do have the um, the income. We do have the output variable as well. We do have the target variable as well. It's called labeled data. Labeled meaning we know the value of the target variable as well. Okay, it's called supervised because we know the value of the target variable. Those are all the same meaning. Okay, so neural networks represent a supervised learning method requiring a large training set of complete records. So I'm saying we have like 10,000 people, or we have 10,000 records, and they're complete, meaning we know the income as well, okay, including the target variable. As each observation from the training set is processed through the network, an output value is produced from the output node. So we know, let's say we were doing this for income. So we do this whole process that we just finished describing, and we get an output. And then he also described how you can translate that output into like an actual income. Now, the output that we get is not likely to be the actual true income of that person, right? We randomly selected the weights, and we did this whole process. It's very unlikely that what we get as an output is going to be the actual. Remember, all these weights are randomly selected, and we go through this whole process of calculating the inputs here and spitting them out here and da 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 da, and we get an output here, and it's very unlikely that that's going to be the actual income of this particular person that we just input their data, whose data we just input. Okay, so there's going to be a difference between the true income and what we predict for that particular person from that particular labeled example. So this output variable value is then compared to the actual value of the target variable for this training set observation, or for this particular person. And the error, so there's kind of an error, right? What we predicted versus the actual income is calculated. This prediction error is analogous to the residuals in regression models. To measure how well the output predictions fit the actual target values, most neural networks use the sum of squared errors. So we take the actual minus the output, we square it, and we do this for all the pieces of our data. So if we had, like I said, 10,000 records where we had the actual target values, we could calculate actual minus output for each of those and square them and sum them up. Where the squared prediction errors are summed over all the output nodes and over all the records in the training set. The problem is therefore to construct a set of model weights that will minimize the SSE. So we want to minimize our error. And what we want to do is construct a set of model weights, a set of those weights. We talked about the weights, and this is all part of our model, so we can call them model weights. But anyway, to construct a set of weights that will minimize. So what we want to do is we're going to adjust the weights. We set them originally randomly, and we're going to adjust them. Okay, let's come back.